when we are dealing with a single variable function, like in this graph, we can create a tangent line at this p0 like this, where the equation of the tangent line is going to be written as y is equal to the mx plus b, where the m can be found as the slope of this line, which is the derivative of this function at this point, x0. So let's say this point has the coordinates x0 and y0. So we could use this tangent line for many purposes, and one of the most important purposes for making this tangent line was to approximate the curve with the lines, right? So we can approximately find the points around this point using the tangent lines. So we would like to now build the tangent planes on a surface. So when the surface is given as a multivariable function, z is equal to the f of x and y, at some point p0, we would like to create a tangent plane, right? So in order to do this, we're going to use the similar ideas as before as for the single variable function. So let's say we're given some surface z is equal to the f of x and y, and we would like to create a tangent plane at this point, p0. So if the two coordinates of this p0 are given, x0 and y0, we can find the third coordinate, right? So in 3D, it works in this case. So previously, if I would like to find the height of the function, I just need to choose this point, x0, right? Then I need to substitute this to this function, and it gives me the y0. So in the 3D now, it works in this way. So I need to choose the x0 and y0, and on the intersection of these 2 points, this function f of x and y is going to give me the height of the surface, right? This is going to be f of x0 and y0. It's going to give me the height of the surface at this point. So in general, we can write down the equation of the plane in this form. So a multiplied as x minus x0, b multiplied as a y minus y0, plus c multiplied as a z minus z0. If I divide all the terms of this equation to the minus c, I could get this equation, right? So I can denote this term as the a and this term as the b to write down the equation of the surface in the form as z minus z0 is equal to a multiplied as x minus x0 plus b multiplied as a y minus y0. So now, at the moment, let us just fix the y to be equal to the y0. So let's say we are not changing the y, so we are fixing the y to be equal to the y0 always. So in this case, we're going to have this kind of a plane where this side, we are going to change the height of the surface only in the x direction, right? Since the y is fixed. Okay, so since the y to be equal to the y0, if I substitute this to this equation, this term is going to vanish, and what I'm going to have is z minus z0 is equal to a multiplied to the x minus x0, right? So if you remember, so the equation of the tangent line was very similar to this, right? So it was y is equal to the mx plus b, where this coefficient before the x was the slope of the tangent line, and we can find this by taking the derivative of the y with respect to the x, right? Similarly here, so I can take this a as the slope of the tangent plane in the x direction, and I can find this by taking the partial derivative of the z with respect to the x. So this is going to be the a. Okay. So similarly, if I fix the x to be equal to the x0, and using the equation of the line of the plane a to be equal a multiplied to the x minus x0 plus b multiplied to the y minus y0 is equal to the z minus z0, by substituting x to be equal to the x0 to here, I can obtain the equation b is equal b multiplied to the y minus y0 is equal to the z minus z0, which is very similar again to the equation of the line, where this coefficient b before the y is the slope of the line, right? And we can obtain this b by taking the partial derivative of the z with respect to the y. So if I substitute the a and b, we can obtain the equation of the plane in a form. So the partial derivative of the z with respect to the x multiplied to the x minus x0 plus the partial derivative of the z with respect to the y multiplied to the y minus y0 is equal to the z minus z0, is the equation of the plane at the point P0 with the coordinates x0, y0, and z0. So if we're basically given the surface with the equation z is equal to the f of x and y, and the point with the coordinates, we can obtain the equation of the plane using this equation. So this was like a intuitive derivation of the equation of the plane. So now we would like to do is we would like to try to get this equation more mathematically, more algebraically, I would say. So when we fix the y to be equal to the y0, and if I cut this, I can look to this curve in the 2D, right? Where I'm changing the height of the surface only in the x direction, right? So let me do this. So when I fix the y to be equal to the y0, so I can change the height of the surface only in the x direction, right? So this is going to be like this. So let's say we've got some point P0 with the coordinates x0 and z0. So y0 is fixed already, right? So depending on where I am on the x, I can change the height of the surface. So the same thing for when I fix the x to be equal to the 0. When I fix x to be equal to the x0, the height of the surface is changing only in the y direction, right? So I can look to this curve in the 2D. So in this case, it's going to be y and z curve, right? So there is a curve. And this is changing only in the y direction since x is fixed, right? So again, so this is going to be at some point y0. I've got this point P0 with the coordinates y0 and z0. So what I would like to do is I would like to create a tangent vector here, and I would like to create a tangent vector here, another tangent vector. So graphically it would be like, so the tangent vector in this direction and the tangent vector in this direction, and by multiplying them as a cross product, I could obtain the perpendicular vector to both of the tangent vectors, which could be a normal vector of the tangent plane, right? So now let's try to get these two vectors. So if I would like to obtain this tangent vector, v1, right? So I know that the slope of the v1, the slope of this vector v1 is equal to the derivative of the surface with respect to the y, right? At this point, at the point x0 and y0. So therefore, I can write down the v1 vector as j plus the derivative of the z with respect to the y multiplied at this point x0 and y0 multiplied to the k. So the same thing for this vector. So if I'm given this vector v2, the slope of this vector v2 is the partial derivative of the z with respect to the x in this case, at this point x0 and y0. So I can obtain this vector v2 by writing this I plus the slope of this line, right? At this point x0 and y0 multiplied to the k. So I obtain these two vectors with the components, and I can multiply them as a cross product in order to get the normal vector, right? So the normal vector is going to be v1 vector, cross product is a v2 vector. So in order to do this, we need to find the determinant of the following matrix, where the first row I would like to write down the I, j, k vectors. On a second row, we need to write down the components of the second vector, the first vector v1, right? So there is no I, so that is why the first component is 0. So the coefficient before the j is 1, and the coefficient before the k is dz dy. So on a third row, we need to write the components of the v2 vector. So there is I here, and the coefficient before the I is 1. There is no j, it means that coefficient before the j is 0, and the coefficient before the k is the partial derivative of the z with respect to the x. So now we need to find out the derivative, the determinant of this matrix. In order to do this, I would like to cross out the I and write down the determinant which is left. It is 1 dz dy 0 dz dx minus j multiplied to the matrix which is left by crossing out the column and the row where the j is located is going to be 0 1 dz dx plus the k multiplied to the determinant of the matrix obtained by crossing out the row in a column where the k is located is going to be 0 1 1 0. So if I find the determinants of the 3 matrix, I would obtain. So dz dx multiplied to the I, right, minus, or plus in this case, dz dy multiplied to the j, right, and minus k. So the normal vector of the tangent plane has the following coordinates. So it's going to be dz dx, dz dy, and minus 1. So do you remember that we used to write down the equation of the plane in general as a multiplied as x minus x0 plus b multiplied as y minus y0 plus c multiplied as z minus z0 is equal to the 0, where a, b, and c are the components of the normal vector, right? So I just need to substitute this was the a, this was the b, and this was the c. So if I substitute them, I would obtain the following result. So the partial derivative of the z with respect to the x at this point, right? At the point x0, y0, multiplied to the x minus x0, plus the partial derivative of the z with respect to the y at this point, x0, y0, multiplied to the y minus y0, multiplied to the minus 1, multiplied to the z minus z0, so that I can write this as a z minus z0 on the right hand side. So this is going to be, again, the tangent plane's equation at the point P0 for the surface Z. So let's do an example of calculating, of creating this tangent plane for a surface. So the surface is given as equation tx squared plus y squared, and we would like to create the tangent plane at the point 1, 1, 3. So in order to do this, what we need to do first is we need to find the partial derivative of the z with respect to the x, right? When we take the partial derivative of the z with respect to the x, so we fix the y's, right? We look to the y as a constant, right? So the derivative of the tx squared is going to be 4x, and derivative of the constant is going to be equal to the 0, right? So we need to evaluate this at the point 1, 1. So if I evaluate this, it's going to be 4. So derivative of the z with respect to the y, it's going to be, so derivative of the tx squared is going to be 0 because x is fixed, x is considered as a constant, plus ty at the point 1 and 1, it's going to be 2. So now we just need to substitute this to the equation, so the general equation in this equation, 4 multiplied to the x minus 1, where x0 is 1, plus t multiplied to the y minus 1, where y0 is 1, is equal to z minus 3. If I open up the brackets, I could get 4x minus 4 plus ty minus t is equal to the z minus 3. From here, I can obtain that the z is equal to the 4x plus ty minus 3 is the equation of the tangent plane to this curve at this point.